Hello, it's Stat135, Lecture 18. Last time we started section 11.1, 11.2, comparing the means of independent normal populations with the same variance. There were two cases, sigma squared known and sigma squared unknown. Sigma squared known is a two-sample z-test, and sigma squared unknown is a two-sample t-test, unless n or m are very large, in which case you can approximate it by a t-test. We introduced the pooled sample variance for our t-test. Today we're going to remove the assumption that the two variances are the same for the two populations, and we're also going to do power calculations. So in section 11.2, as previous, we assumed that x and y both have the same variance. If we remove this assumption, then we're going to need a new estimator for the standard error, and we're going to use the sample variance over n plus the sample variance of y over n over m, and we can see that it's unbiased. But what makes it great is that the test statistic, when we use this as our standard error, is approximately a t-distribution whose degrees of freedom is given by this terrible formula here on page 428 that you don't need to memorize, but you do need to know about it, and usually you use it in R. So you'll have a homework problem with this. Here's an example. You have 50 rats randomly divided into two groups of 25 each. The rats in one group are given steroids. The rats in the non-steroid group have an average time of 10 seconds with an SD of 2 seconds. The rats in the steroid group have an average time of 9 seconds with a different SD 5. So what's the SC of the difference of the two averages? Calculate the test statistic for testing the null hypothesis that steroids make no difference, and what's the p-value of the test. And we're going to, because the SDs are different here, we're going to use the formula from Rice that we just mentioned, and I'm telling you that it is 31 degrees of freedom, which is large, so you can just approximate this by a z-test. Here's a picture reminding you that the t-distribution becomes a z-distribution as the degrees of freedom increases. So we have the standard error, 1.08. We have a two-sided alternative, and we find a test statistic then of minus 0.93. Now, to calculate the p-value, remember that we're rejecting, because it's a two-sided test, we're rejecting for absolute value of t large, which, since t is symmetric about 0, means that we are looking for the probability that either t is less than minus 0.93 or t is greater than 0.93. And we can, this is essentially 2 times p norm of minus 0.93, which is 0.35. Now 0.35 is larger than your alpha, 0.05, so we would not reject the null. In other words, we accept the alternative. Now, we don't have any evidence, hence, that steroids make rats run differently. Oh, I'm sorry. So we don't reject the null. In other words, we accept the null. So we don't have any evidence that steroids make rats run differently than non-doped rats. I didn't have time to do this in class, but actually this is a very good exercise to test your understanding of what's been going on, and duality of hypothesis testing in confidence intervals. So you might want to shut off this video and just verify that the two-sample t-test at the level alpha of null hypothesis, that the difference, the population difference of the means is 0 versus the alternative that the difference is not 0, that we accept the null if and only if the confidence interval for the difference of the population means contains 0. So this is exactly the same proof as what we did earlier for when I introduced the duality. So I won't discuss it here, but I did write out the solution and check it line by line, make sure that it makes sense to you. Then we talked about power. So determining power is an important part of planning an experiment in order to determine how large a sample size you should use. So let's assume that sigma is known. Sigma is the same for both populations, and that n is equal to m, just to make things a little bit easier. So we have a one-sided alternative where mu x minus mu y is delta, which is some positive number. And so the picture that we have, I have here two normal distributions, and the green shaded region is alpha, the purple shaded region is the power. And the rejection region is z alpha times sigma square root of 2 over n. The reason that you have the sigma square root 2 over n is because this is the distribution for x bar minus y bar, which has not been normalized. If it was normalized, the rejection region would be to the right of z alpha. But if I were to normalize this, say subtract 0, divide by the standard error, then the cutoff would be z alpha. So we can compute the power, and this formula for power allows us to examine the effects of delta, alpha, sigma, and n on your calculation. And I've just drawn here two figures to help us. One figure is showing you z alpha as a function of alpha, the level of significance under the null distribution. And then the other picture is a graph for 1 minus the CDF of, say, x. So that runs from 1 to 0. And so it should be, just check the formula and you should be able to see that as delta alpha and n increase, the power increases, but as sigma increases, the power decreases. So here's an example of a typical power calculation. Suppose n measurements are taken from a treatment group and independently n are taken from a control group, and SD of a single measurement is sigma is 10 for both groups. How large should n be so that the test, your usual one-sided test here, has power 0.7 if your delta is 1 and alpha is 0.05. So you just follow the steps. Just note that Q norm undoes P norm. So to solve for n, we need Q norm of 0.3. And we find n is 941. Okay, that's the show for today. I hope you have a great day, and I'll see you on Friday.